Okay, so this is the first part of 4.1 notes here. I'm going to try to move through this pretty quickly, but there are a couple new calc concepts, so make sure you guys do pay attention to that part. But otherwise, hopefully a lot of this section is review over energies and work and things like that. But anyway, we'll discuss three different forms of energy in this chapter: kinetic, potential, and thermal energy. Really, the only context we see thermal energy is the work done by friction. We know that when we have energy lost, it's not actually lost, right? It's just converted to another form. So in all of those situations where the kinetic energy gets lost, or maybe the potential energy gets converted, right? A lot of that energy is then going to thermal energy, which is really just heat. So we'll see that pop up from time to time. But otherwise, you've got the rest of these bullets here, so I won't spend a whole lot of time going through these. Just make sure you are comfortable with what the system is. It's the objects in question, the environment, anything surrounding it. Keep in mind that energy is never created or destroyed, it's only transformed. And then energy may be transferred to or from a system by forces acting on it. So we'll see all of that pop up in a little bit more detail moving on, but again, you have all of those, so I won't waste much more time than that for now. But anyway, so let's go back and just kind of revisit some of what you already know, right? Again, you guys have already got a pretty solid understanding of kinetic and potential energy. So how do we calculate the kinetic energy of an object? Well, obviously you've got the equation sheet you're able to work with as well, but hopefully we all remember the fact that the kinetic energy is 1/2 mass times velocity squared. Right? So I've got the kinetic energy, which is 1/2 mass times velocity squared. Keep in mind that that is a scalar. That is not a vector, it is a scalar, which means the direction does not matter. So if I ask you for the kinetic energy of an object that's in projectile motion, I don't care about the horizontal and vertical components of it. I just want to know how fast is it moving at that location, and I use that entire velocity as my v there. So don't break up energies into components, right? How about gravitational potential energy? Hopefully, again, we all remember that. The potential energy due to gravity, sometimes we see that as U of g instead of PE, but it's just mass times gravity times height, right? So mgh or mg delta y if you prefer. But it's just the mass of the object times gravity times the height. So then what about this? If an object is in free fall, how do these energies relate to one another? Well, there is one important concept here, right? It's what's going on in free fall. Well, we know if it's in free fall, the only force acting is the force of gravity. And the force of gravity is also essentially defining my potential energy due to gravity. So if I think about it, if I take an object and I drop it, it initially has some potential energy due to gravity based on its height, right? We know in terms of kinematics, as I drop it, it's going to pick up speed, which means as I drop it, as it begins to fall, it's now starting to gain kinetic energy, but it's starting to lose potential energy because of the loss of height there. So as it becomes a closer distance to the ground, the potential energy decreases. So what's the relationship between these two? Well, it's a one-to-one relationship. If it's in free fall, if the only force acting is the force of gravity, if there's no air resistance, drag, or anything like that, then however much potential energy is lost, right, that equals the amount of kinetic energy that's been gained. So that is something to be very comfortable with. Obviously, we'll see that worked in several examples as we go throughout this chapter. But if we start with potential energy and you lose that potential energy, it goes to kinetic energy as long as there are no outside forces acting. And so again, that's going to be something we see throughout the chapter. And then finally, I want you guys to think about this equation in the context of energies, right? So we know that this is a kinematics equation, right? That's one of our three big equations we work a lot with. But how can I represent that in terms of energies? Well, if I look at this, right, I've got v final squared, v initial squared, 2a delta y. Well, I could start by making this my change in y, right? So my y final minus my y initial. I also know that the acceleration in free fall would be negative gravity, right? It'd be negative 9.8. So I could rewrite this equation as v squared equals vi squared minus 2g, and then my y final minus my y initial. So then if I distribute the negative 2g to each of those, I've got v final squared equals vi squared minus 2g y final plus 2g y initial. And then if I do just a little bit more magic here, what happens if I take everything and divide it by 2? Right? Obviously I'm not doing anything to change the equation, just dividing it by 2. And then what happens if I also take everything and multiply it by the same constant of the mass? Well, what I end up with then is 1/2 mass times velocity final squared equals 1/2 mass times the initial velocity squared, right, minus mg its final position, and then plus mg its initial position. And then if I clean this up just a little bit more and move the the final over to the other side, so I'm just going to add that quantity over, what I end up getting here is my 1/2 mass times final velocity squared plus mass times gravity times the final position squared equals 1/2 mass times the initial velocity squared plus mass times gravity times the initial height. And so really what I want you to walk away with from this is my kinetic energy, right? So this is my final kinetic energy. This is my final potential energy. This over here was my initial kinetic energy. And this over here was my initial potential energy, right? So what this is showing me is this just illustrates the conservation of energy, right? Whatever my total energy afterwards, that's equal to my total energy beforehand, right? So the reason I did this, one, obviously it's good to see, but the other reason that I did this is when you see this kinematics equation and when you see the conservation of energy, really we're not doing anything new with the conservation of energy. We're just rearranging it in a way that's a little bit more accessible for working with energies. So anyway, you're familiar hopefully with both of those equations as it is, but sometimes it is good to see the relationship between the two. So again, these two are really the exact same equation, just represented differently using mathematics. But anyway, we'll continue on from there. So this would hopefully be a pretty easy question for you guys to solve. You are welcome to pause and go ahead and do it on your own first, and then just check and make sure that your answers agree with me. But again, hopefully this one's pretty straightforward. I don't think you guys would have any trouble with it. But anyway, Jimmy uses a slingshot to shoot a 20 gram. Do keep in mind it's 20 gram, and we typically want kilograms, right? So he's shooting 20 gram pebble straight up with an initial speed of 25 meters per second. How high does the pebble go? Well, obviously I could do part A using kinematics, and there's nothing wrong with that. However, I do want us to start to think about the context of energies, right? So when the pebble is first released, if I define that as the height of 0, when the pebble is first released, then all of its energy would be kinetic energy, right? Whereas at the highest point, we know that the pebble is going to momentarily pause, and so at the highest point it would have a kinetic energy that is equal to 0, which means all of its energy is now gravitational. Right, so what that tells us is, because those are the total energies at those locations, then my kinetic energy converts to my final potential energy. Right, so I could set this up using the entire equation that I just saw. You could set that up and say, you could do the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. But you just realize as you go through this that the initial potential energy is 0 and the final kinetic energy is 0. So really it's just the initial kinetic equals the final potential, which is what I have over here. But anyway, hopefully again pretty easy. So 1/2 mass times velocity squared equals mass times gravity times height. As you can see for this particular part, the mass is completely irrelevant, right? So it'd be 1/2 the velocity of 25 squared equals 9.8 times the height. So then just solving that out, I solve for that and I get h to be about 31.9 meters high. So I've got the height that it reaches. Again, if you did kinematics, you would find that it is the exact same answer. And then part B, I did just want us to go back and kind of review the energy bar charts, right? So they ask us to do it at 3 different locations. What is it right after it's released? What is it at half of its maximum height? And then what is it at the highest point? Well, let's start with right after it's released and at the highest points, because those are the easiest parts, right? So if I've got my energy bar chart, right, I know I've got 2 different forms of energy. I've got kinetic energy and I've got potential energy, right? Right after it's released, I know all of its energy would be kinetic energy. So I'm just going to define this as the total amount of energy, right? So all of that energy would be kinetic. Granted, if this was on an AP exam, I would label this as either the numerical value or at least using the variables of 1/2 mv squared, right? I'd make it very clear what the total energy is up here. So if you wanted to calculate that, you could do so. I'm not going to take the time to do that, but it would be very good to do that if you were taking a test. But anyway, so the kinetic energy is all of the energy. We don't have any potential energy, right? So that's just down here at 0. Then let's think about at the end of the trip. Well, again, at the highest point, right, we know that the potential energy would be all of the rock's energy, right? So now its kinetic energy would be 0, and its potential energy would be the highest. So it would go up to that same measurement. And it is worth noting that you could label that then as the exact same thing. So even though we know that this is also mgh, I could still call this 1/2 mv squared, because it should be the same number as long as there's no air resistance. Right? So then the final situation. What about halfway up? The question that I do want you to pause and think about for a second is, would it be exactly half, and how do we know? Right? So would it be exactly half of the energy for each, and how do we know? So I've got kinetic energy and potential energy, and again, hopefully you've paused it and thought about that a little bit. The answer is it would be exactly half, and the reason that I know that is if I focus on the potential energy, which is mass times gravity times height, if I were to cut the height in half, wouldn't I cut this entire number, this entire quantity down here in half? Right, so if I focus just on the potential energy, then it's clear to see that half the height, it is going to have half potential energy and then half kinetic energy as well. Right, so this would be at 1/4 mv squared, because that's 1/2 of 1/2 mv squared. But anyway, like I said, if you could get the actual number for that, awesome. You definitely could use that to label these two. But hopefully part B is also pretty easy to work through. Okay, so then the final part of this first video, and this is very, very important. This is one of the new things we see using some calculus, and I do want you guys to be comfortable with this derivation as we go through it. So anyway, we can reach the same relationship for kinetic and potential energy, so the conservation of energy, by using the net force and calculus. Right? And the way that we're going to do that is we're going to start with this equation right here. And actually, specifically, I'm going to start with mass times acceleration, which represents the net force, right, equals, I'm going to go ahead and define it as negative mg, since we know gravity is pulling downward, and gravity is typically defined as negative. The other key thing here is, just like we've started to see, think of the acceleration not just as a, but think of the acceleration as the derivative of velocity, right? So acceleration is really the derivative of velocity with respect to time. So it's just dv over dt, right? The reason I want you to think about that, if I go ahead and break this up, so it's now m times dv over dt instead of my acceleration equals negative mg. Now that I'm thinking of it through this context, makes it clear that maybe I could do an integration on both sides. Now the difference is, you guys have seen that we could multiply both sides by dt, right? What I could do here is I could multiply both sides by dt, and then I would get mdv equals negative mg dt, and I could integrate both sides, which would give me mv plus c, and then this would give me negative mgt, right, plus c. But this value over here really doesn't have any meaning for us, particularly in the context of energies. So I'm actually not going to do that approach. Right, so this is where it gets a little bit trickier, but I'm going to take one other step in here. Like I said, I do want you guys to get comfortable with this step. It's not terribly difficult once you've done it a few times. But I'm actually going to take dv over dt, and I'm going to break that up into a third-party variable. And what I mean by that is I'm going to break this into dv over dx times dx over dt. Notice, as long as I choose the same value here and here, it doesn't matter what variable I choose. Right? I can make that dx, I can make that dy, I can make that dw, whatever I feel like making that. Right? But if you just look at the multiplication property right now, because I'm multiplying it on top and bottom, it doesn't actually change the value of this. The reason that we do that is, what is dx over dt? Well, dx over dt is really just velocity. Right? So coming back over to my equation, what I really have is mass times, again, I'm going to make this the entire quantity, so dv over dx times dx over dt, where again I really know that this is just the velocity, equals negative mass times gravity. Right, so that's what I've got so far. I am going to go ahead and substitute dx over dt as the velocity, so I've got mass times dv over dx times the velocity equals negative mg, and then I'm going to multiply both sides by dx. So now I have mass times, I'm going to go ahead and move the velocity out front, I've got mass times velocity dv equals negative mg dx. Now if I integrate both sides with respect to the appropriate variable, right, this ends up being, well, I have to integrate it with respect to v, which means I need to add 1 to the power and then divide by it. So it ends up being 1/2 mv squared plus c equals, over here, this ends up being negative mgx plus c. I'll finish this out in the next part.